In this next video, we're finally ready to define the rank of a matrix. We'll do that not immediately. First, we need to define the related notions of row rank and column rank. And so for those, we'll begin again with the assumption that A is an arbitrary m by n matrix. And we make the following definitions. The row rank of A is defined to be the dimension of the row space of A, while the column rank of A is defined to be the dimension of the column space of A. So we associate two integers with an m by n matrix, its row rank and its column rank. Those are the dimensions of its row space and column space, respectively. Let's start with an arbitrary m by n matrix A and discuss its row and column rank. So, how do we find, for example, the row rank of A? Well, we have to find a basis for the row space of A, and then just count the number of elements in the basis. So let's do that. To find a basis for the row space of A, we recall from the previous video that we first move to row echelon form from A to its row echelon form B. And then from here, we pick out the non-zero rows of B. Those give us a basis for the row space of A. Here's the picture. We go row echelon form down to B, and then to get a row space basis, we just choose or pick off the non-zero rows of B, and that gives us a basis for the row space. And therefore, the row rank is equal to the number of non-zero rows of B. Now, how about the column space? Well, remember, to find a basis for the column space, we look at the columns with leading ones in B, and we find some columns here. Now, we may choose corresponding rows up here in A to find that basis, but it still follows that the dimension of the column space is equal to the number of columns with leading ones in B, and that then is the column rank. Number of columns with leading ones in B. But let's remember now a key observation we made earlier. If B is in row echelon form, then for any matrix in row echelon form, the number of non-zero rows is always equal to the number of columns with leading ones. These numbers are always equal, and therefore the row rank is always equal to the column rank. And this is true for any matrix A. You can calculate the row rank and calculate the column rank, and those will always be the same number. We saw in an example in the previous video that we had a 3 by 3 matrix for which the row rank was 2 and the column rank was 2, and the coincidence of those ranks is not a coincidence, it's always the same. And that's our first significant theorem in this video. Here's the theorem. If A is an arbitrary m by n matrix, then the row rank of A is always equal to the column rank of A. So we make a new definition. We define a new number called the rank of A, which is defined to be either the row or the column rank, since they're always equal anyway. Before moving on to the next major theorem in this section, let's pause for a moment and make an interesting and helpful observation about the rank of a matrix. Suppose A and B are row equivalent. So remember what this means. We can obtain A from B by left multiplying B by a sequence of elementary row operations. Each one of these performs a row operation on B. We observed earlier that if A and B share this relationship, then they have the same row space. Multiplying B on the left by an elementary matrix does not change the row space of B. So we observe that if A and B are row equivalent, they have the same row space, again, because this is row equivalent to this. And so the row rank of A and B must be the same, but now we know that the row rank is just what we call the rank, and so we can conclude that the rank of A is equal to the rank of B. If A and B are row equivalent, they have the same rank. The same is true, of course, if we replace elementary row operations with elementary column operations. We will omit some of the details that we included just a moment before. If A is column equivalent to B, that means A can be obtained from B by a sequence of column operations, that is, multiplying B on the right by elementary matrices. And by the same rationale, doing so does not change the column space. And therefore, if the column space of A is equal to the column space of B, then the column rank of A equals the column rank of B. But again, we just now call that the rank. And so what we've shown, putting it together, is that if A is equivalent to B, that is, A can be written as B multiplied on the left and on the right by elementary matrices, then the rank of A is equal to the rank of E1 through EK times B times EK plus 1 through EL. But we know since this matrix is row equivalent to this matrix, they have the same rank. And since this matrix is column equivalent to this matrix, they have the same rank. And therefore, the rank of A is equal to the rank of B. Now, conversely, let's begin by supposing that A and B have the same rank. Let's call it R. Now, if A has rank R, let's take A all the way down to reduced row echelon form. That is, there exists a sequence of row and or column, perhaps possibly both, operations which take A to the following matrix, which looks like an R by R identity matrix in the upper left-hand corner, followed by submatrices of zeros everywhere else. And of course, if the rank of B is R, the same is true for B. A and B both have the same rank, then they're both equivalent to this matrix. Well, on the left-hand side, if A is equivalent to this matrix, this means there are invertible matrices P1 and Q1, such that P1A Q1 is equal to this block matrix. These P1s and Q1s are just the products of elementary matrices over here and over here. And of course, similarly, the same thing is true on the right for B. If B is equivalent to this matrix, then there exist invertible matrices P2 and Q2 such that this block matrix is equal to P2B Q2. And then we can equate this matrix and this matrix, left multiply by P1 inverse, right multiply by Q1 inverse, to obtain the following expression for A. And then noting that this is another non-singular matrix, and this is another non-singular matrix, we can conclude that A is equivalent to B. And so we have the following relationship, that two matrices are equivalent if and only if their ranks are the same. Here's the theorem. Let A and B be M by N matrices. Then A is equivalent to B if and only if the rank of A is equal to the rank of B. Now, in preparation for the next significant theorem in this section, let's summarize three subspaces that we've seen that are associated with any M by N matrix A. There are three important subspaces we have now to keep track of. First, there's the row space. This is the subspace formed by the span of the rows of A. Then there's the column space. This is the vector space formed by the span of the columns of A. And finally, one we haven't seen for a few minutes, there's the null space of A. This is the vector space of solutions of the homogeneous system. Now, these are three different subspaces which don't necessarily have anything to do with one another, but there are relationships between all three of them. We've already seen a relationship between the row space and the column space. That is, the dimension of these two is always the same, and that was a major theorem. Now we'll see a relationship between these two and the null space of A. Let's recall again how we find that null space. So we set up the homogeneous system, we move down to augmented matrix form, and then we reduce that to row echelon form, or reduced row echelon form if you like. We'll write reduced row echelon form to obtain a matrix here. Now let's pause here and remember what we do. To count the basis for the null space, we look at columns that lack a pivot. So each one of these columns here that lacks a pivot contributes one basis vector to the dimension of the null space. What about the columns left over, the columns containing a pivot? Well, as we remarked before, when we're in reduced row echelon form, either a column contains a pivot or it doesn't contain a pivot. That is, either it corresponds to a pivot variable or it corresponds to a free variable. If it corresponds to a free variable, then it contributes a basis vector to the null space. And if it corresponds to a pivot, that is, if it contains a leading 1, then it contributes a vector to the column space of A. So let's write this equation down. Each column either contains a leading 1 or it does not. So the number of columns with leading 1s plus the number of columns without leading 1s is of course the total number of columns, and if A is an m by n matrix, then there are exactly n columns. So that's pretty obvious. But now we remember what each of these summands is. The number of columns with leading 1s is precisely the dimension of the column space of A, that is, the column rank or the rank of A. And the number of columns without leading 1s is the dimension of the null space of A, or what we call the nullity of A. And so we have established the following major theorem, that the rank of the matrix plus the nullity of the matrix is equal to the number of columns n. This is sometimes called the rank plus nullity theorem.